Hello developers, let's get developing. So now we're gonna take on part 2 of the task 12. You can see on the hour that it's actually... Oh, you can't. Let's do that. Oop, it's 15th of January, so we didn't manage to solve this the proper time around. So this means that now we will have to take care of that. And so far, I think this is the hardest task that was because we have some input. And let's find the proper input for that day. Day 12 and day 12, the second star. So we have this thing as a demo. Actually, this thing as a demo. So we need to play around with it. And the problem is that we need to find all the possible configuration, all the possible ways that we can replace the question marks with something so that that something actually works. We implemented for the first part a totally brute force solution. When we actually only count the patterns at the very end, we will be generating all the possible patterns for the question marks, which means that if we have something that has, let's copy, where are you, this. If we have something that has 3 question marks, we're gonna generate all the 8 possible combination, and if we have something that has 1, 2, 3, 4, 5, 6, 7, 8, 9 question marks, we're gonna generate all the 520 options. And if we have something that has 20 question marks, we're gonna generate all the million options. And then check them one by one. If it matches, count plus plus. However, as soon as I did that, and I've actually run that, that is for part 1. Part 2 is still not implemented, so we have the brute force option. And that was the one that was actually running all the other days when I ran all the tasks simultaneously, subsequently. So for this input, it runs at 3 milliseconds since we don't have a lot of cases. But for the big input, it will take some more time. The result for this should be 21. And for our real input should be 7753. So it actually gives us the correct answer in 4 seconds. After I did that, I went through the code a bit and said, well, let's think a bit about this. What happens? So this algorithm. So we're gonna get the first question mark index, and if we don't have a question mark, well, then do the brute pattern match checking. Otherwise, find that question mark, replace it with a hash, and recurse on it, which means that we are splitting each time into an option that has a hash. We're splitting the world into one when the hash happened and one when the dot happened. And we're recursing and recursing and recursing. So this will have the exact same behavior as the for loop brute force. But since this is using recursion, I definitely, all of my feeling and knowledge said this is gonna be slower. Until I ran it. So we had somewhere around 4 seconds for that. for the big input and this is totally identical behavior to the previous one, so it should be at the very best the same or slower, but it's actually faster. So that's once more the my first rule of performance optimization is checks out, because the first three rules of performance optimizations are measure, measure, and measure. We thought that this would be slower. It's not. Okay. Maybe some other optimization happens. I don't know, some kind of a tail call recursion. I don't think that applies, but you can't argue with the result. So that's great. But then I tried to actually do some proper optimization, because this is not an optimization. This is the exact same brute force algorithm, just implemented in a bit nicer way. But I wanted, since this pattern matching that checks whether our pattern matches the groups, is actually only works if we don't have any question marks. If we have question marks, this doesn't work. And I wanted to make one that will be a bit nicer, that will actually, if it has a question mark, it will answer, I don't know. But up to that first question mark, it will actually check. So if we have, for example, this situation, it says this, okay, it's okay, it's okay, it's okay, it's okay. Oh, we have a question mark. Okay, I don't know what happens after this. But so far it will be okay. But if instead of replacing it like this, we replaced it like this, it will say, oh no, this is not okay. This is not okay. So it's not the most resilient method. It's not gonna trim it too much, but it will trim it some. And note that if we are able to trim it, each question mark actually separates the world in two, duplicates the world. And if we are able basically to exclude 1/4 of all possible situations, because this works, this works, this works, and this doesn't work. Then out of separating with those two question marks, we're not separating into four options, we're separating into three options. That's a lot less actually when you count that it's actually exponential. So I had some problems debugging this function, as I expected to have, since this is very weird matching, so we need to think of all the details, all the special cases, but I think I got it kind of down. So let's see once more how our check is right now, how our code is right now. So we're again getting the first question mark. If we don't have question marks, do the proper check. If the proper check matches, it's 1. If otherwise, it's 0. Since if we don't have question marks, we have only those two options. It either matches completely or it doesn't match. We cannot say it maybe matches. Why? It doesn't have any question marks. And then again, we do the splitting of the worlds, but with a dot and a hash, but only if we don't get that this is impossible. If we get that this pattern doesn't make sense, then we say, okay, we're not gonna do that. We already know what the result is for a pattern that doesn't make sense. It's 0. And after that, we just return that. So let's see how this behaves. Once more, the non-recursive one was 4 seconds, the recursive one was 28:46. Let's save this version and then let's copy it over with this version. So I can do undo redo. And the one that is improved, well, it runs in 94 milliseconds and gives us the wrong answer. We actually have the answer for part 1, but now we're optimizing because the part 1 and part 2 will have the exact same algorithm. I want to optimize it the heck out of it. So let's see if it gives us the correct answer for this one. It says 6. It's definitely not 6. But let's change the bit. So instead of summing it, we're gonna map it, and we're gonna console log it, the result, and then we're gonna just sum it for the result. Let's see what we're doing wrong. So it says that the first person has one wallet, and then instead of 4 wallets, actually it says, no, you don't have any valid things. But it kind of does. So what we will need to do is to debug. So I will just take this option, since this is not providing the desired result. Yeah, I thought that I got all the bugs out. Apparently, I didn't. Let's see. So we need a breakpoint here as well. And now we actually need 12 to attach to it and see what happens where. Why these 2 question marks don't get calculated correctly. So our pattern is question mark, and so on. So the index should be 1. Yep. So now our hash pattern should be the same thing, only with a hash in that place. Does the pattern so far matches the groups? Actually, I won't put this on now. It's so we're skipping all the dots at the beginning because in general we don't care about them. If we're done, we're done. So we have a hash and we say we're okay, but the next one is a question mark. So we say we don't know, which means that we need to continue. So then we call this, our pattern becomes that. So I means that we will be calling this with 2 hashes next. Since we're doing a, no, we're calling it with a hash and a dot. Why? Because the 2 hashes failed this check. So this never executed for the 2 hashes. And it's great. That's what we wanted. And then we call it with a hash. And now we should call it with a hash dot. And this is the last time. And we should call it with a hash. And we didn't do that. We backtracked. So breaking this up, restarting it once again, and we need to see what happens when we call it with hash question mark hash. Well, I'm not actually, I started to run day 15 and it said day 15 doesn't exist because I'm on a separate branch off of day 12 because I might totally fail in solving this task. and then you will never get to see this video. So let's see the pattern. Yep. First question mark, second question mark, third question mark. So we should have one more that we need to process. Yep. And now we have hash hash question mark hash hash. Let's see. Do we have a question marks? Yes, we do. Check that pattern. And now we have this pattern. Does that pattern matches the groups? The groups are 113 and we have a 113 pattern. Let's see what happens. Let's see if we return something that we shouldn't. Oh, we're getting here and we have a hash count of 0 and the current group is undefined. Because we run out of groups, we run out of caches, and that's a good thing. But in this specific case, we said, see if the last thing matches. I will add this as a specific case. Otherwise, return this. So this will happen when we end our pattern on a dot, which means a valid pattern on a dot, which means we have processed all the hashes that were before that and processed all the groups as well. If we have a missing group, then it's gonna fail. If we have an extra group, then it's gonna fail. But if we run out of both hashes and groups, we have a match. So, and that's why we have this as well, because this is for the case when we finish on a hash, which means we're still processing the current group and we're still counting the hashes. We have 3 hashes, we have a group of that says it needs 3 hashes, we're golden. If the last group says it needs 2, it's not a match. If the last group says it needs 4, it's not a match. If it's 3 and 3, it is a match. So let's try to run this now. And let's go back to the original demo. We should get 1 for something something. That is definitely available here. 1 for 1 1 4 10. And we got 1 for 1 1 4 10. Okay, that was an issue. Let's do the huge input. So this might take a while. Seven seven 753, and we were supposed to get 7753. So we got the correct value in 111 milliseconds, which is cool. So basically, it might be that this is a viable option for part 2 as well. One way to find out. And that way is actually by writing some code. So what do we need to do for part 2? Let's see. We need to unfold the record. Replace the list of spring conditions with 5 copies of itself separated by a question mark, and replace the list of continuous groups of damaged spring with 5 copies of itself separated by comma. So actually we need to do this. Instead of input, we're gonna map unfolded. We're gonna have to have each row, and each row is contained of pattern and groups, and we're gonna return an object just like that. That is also a row. Oh, and we need to put a parenthesis around this so that it doesn't complain. And we're gonna say that the pattern is something like this. We're gonna have an array that says take the pattern then add a question mark and see that this is type safe. So if I say that I want to add an item, I cannot say Z. It's going to say that's not a pattern. And then we take this thing and we repeat it 5 times. But we need to end with the pattern. So we have the pattern once, twice, thrice, 4 times, 5 times. Remove the last question mark. And the groups are groups. 5 copies of itself with 5 copies of itself replaces separated by a comma. Yeah, that's just a repetition. So that thing becomes this thing with 4 thingies. And let's just check what we're doing first. Unfolded of 0. Let's print this unfolded of 0 dot pattern and a space, and unfolded of 0 dot groups dot join with the comma. So if we're correct and we put in a return 0 here, we might get something. The easiest way to get the wrong answer is to ask the wrong question. So we really don't need this, since the pattern is also an array. We wanted to actually join it with nothing in between. So first of all, this might be correct, it might not be. Let's see if it's what we need it to be, and it's not, because most likely our input is not, and we are working with the not the biggest input in the world. So the first line of the example, which is that, should become that. Let's run it once more. The 2s and the 6s should have been very much a dead giveaway, because we have this line. Let's see if we have that line perfect. After unfolding, the number of possible arrangements are. So, to be honest, I have a suspicion that we might have some kind of way to actually get to from this number to this number. But on the other hand, we have 1, 1, and 1, which transport into 1, 1, and 16. And we have 4 and 4, then transport into this and this. So we will have to do some kind of in-depth analysis of the pattern and whatnot. But anyway, let's try this. So our code for these specific inputs would be just, so we don't need the console log, we take the input and map it into the configuration sums. Let's console log them and let's return them. And we're not using the input, we're using the unfolded input. It seems that the unfolded is correct. And let's see if this finishes like ever for this. It could take a while. It returned 16384, which is the correct value, 1, 16, 2500, 506, 250. It could work, and it wasn't too slow. So I will actually do this. Return this, since a map is also a function, console log processing the pattern, because I'm not so excited about the groups. And see if this thing outputs once a month or once every few seconds. And while we're at it, let's have the index as well. And we'll just put out index +1, since we're starting from 0. Let's see if this is faster than a few minutes. So this is our first attempt at solving this, first attempt at optimization. I have some more ideas where we can do some analysis and whatnot, but oh, that's a lot of question marks. And I feel like I should go off on a smoke break and come back and see whether this thing actually produced anything. Just as a joke, let's... Oh, we also have an extra one of these at the end, so that doesn't matter. But we have how many question marks? Loads. So those are 4. And then we have, how do they get more and more? Oh, and then they vary between that many. So we have 4 and oh, those are 5. 4 and 5, 9, and these are 10. So 9, 19, 29. Yep. 39, 49. And then we have 5 rows for 7. That's 35, 49, and 35. That's a lot. I'm gonna get it wrong, so I'm gonna just do it. 84. So we actually need to calculate something that has a complexity that's on the order of 284 and power that to that power. And of course, assuming It's the sixth one. Let's see what actually happens. It says 1811. So yeah, each time that we put in here two dashes here, two hashes, this will break. So let's say that we, instead of having 2 on the 84th, we have something like 1.5. So you can see that just by eliminating, let's say, a quarter of the possibilities, of the initial possibilities, we kind of reduced, how many is that? 11 orders of magnitude. So these two numbers seem huge, and they are huge. But this one is 11 orders of magnitude, which means around 100 billion times smaller than the second one. It's still 100,000 billion or something like that. No, it's 600 billion, but still it's 100 billion times less than the other one. So it seems that we are stuck on that. Maybe that's a bad example. Or maybe that's kind of characteristic of the items we have. So if that is a bad example, we can just run that into the ground and then brute force on everything else. Just calculate everything else. But if 6 and 7 and 8 and 9 and 10 and 1000 take 5 minutes each to process, then we might have a problem. Okay, let's go for a smoke and let's go for a think. And when I come back, I will see where we've gotten so far. We've gotten up to the number 6. So now it's sometime later and we're still stuck on processing this monstrosity, and I'm quite confident this won't end like ever. Let's kill it and see what we can do for our next optimization. So one thing that we can maybe do is that our code doesn't really care how many things we change and how we change it. Because let's go back to the small input. And yeah, this might be a nice example to take. So we have this, but how many hashes we will need to have total? We will need to have 3 to 1, 6 hashes. But my code so far doesn't really care if we put 17 or so. So what we will need to do is actually take care of how many are we putting in. Are we putting in too many or too few? And will that help? Because at the moment that we enter 6 hashes, we're still trying to add a lot of them, and we're still trying to check what is possible and what is not. So let's maybe do that as well. So we will have type that says, yeah, we're gonna need some cache, but that's for later. Row extra. That our row is actually an interface, so we might, no, it's a type. Let's change it into, or let's use a type. That's the option as well. So that will be something that has everything the row has, but it also have a total hashes or hash count, or we can say how many we actually need. So we need a hash left, which is a number. We can have the quest questions left, and we can have dots left. And these numbers should always be positive or zero. If we have questions left, that means we have a fixed thing that is done. Seems fine. So we're gonna remap this once more. Some more parentheses. We're gonna say take the pattern, take the groups. How many hashes are left? Well, we will need to find. Actually, let's change it up a bit. We will calculate those. So we can see how many question marks it has. How many question marks does it have? So, and how many hashes do we need to have in total? Well, groups dot sum. That's all the hashes that we should have. And how many hashes do we have now? Current. That's from the pattern. Find the hashes. So we can have, and so the questions that are missing, hashes left, are how many we should have minus how many we actually have. That means how many hashes do we need to add. So for this case, we need to add 3 hashes. We have 3, we should have 6. So that means that the number of dot left are the number of question marks minus the number of hashes that are left. So we can say return pattern, groups, hashes left, questions left, dots left as row extra. And now we can just use that in our get for configurations count. But instead of using this, it will be row extra. Actually, yeah, row extra. And now this complains because we will need to update it. We have a hash pattern, and if we have this hash pattern, which means that we will need to change it up. The groups are the same. The hashes left. We added a hash, which means that the hashes left is hash left. Oh, we didn't deconstruct the other ones. Hash left, questions left, and dots left. So this will be hash left minus 1 because we added a hash. The questions left will be questions left minus 1 because we removed a question mark each time, and the dots left is just the same thing. We will need to do the same thing for the dots. And we have hash left is the same, question mark is 1 less, and dot is 1 less. So now we can run some checks here. And we don't need to do this check. We can just say if questions left. Oh, but we do need the QMark index. But we can have it here. But otherwise we can say if the questions left is equal to 0. So right now we're not using that data for anything special. We have the small input and let's check if we broke something. We did. It says get configuration count row. Yeah, unfolded is an void array. Something is still red. Is it? What is this red thing now? Oh, for part 1. Ah. Now we just can't use that. But this might optimize, this will optimize part 1. So we can add input dot. Actually, let's extract this to a method. And if we just do that, which means that we can take this up here. So input dot map row to row extra of row, and then run that and run the result. And now instead of map it like this, we can say, oh, no root certificates, row to row extra. We're not actually using that things for anything. '21 and 525152. I think that is what we needed to find out. So 525152. Yeah. So we didn't break anything. Our baseline is still holding, and the last one still takes a while to actually get it. And I have a feeling that this might come handy in this situation. It won't get handy in the original situation when we had just this, because we weren't able to actually do too much. We just needed 3, so as soon as we do this, for example, and we run out of dashes, this will say this doesn't match because the group is 2. But in this case, we can actually do something like 2, then 1, then 3, and so on and so forth. And I have a feeling that we still won't get run out of hashes and dots. So this might not be as big of a win as I thought at first, but let's see. So if we don't have any question marks left, then we're okay. But if we... How do we use this? We might run out of hashes before we actually do that. So having hash lefts equal to 0. Yeah, we can just add it here. Have this here as well. And we can say this, we will do this if we have more hashes. Otherwise, don't bother with this at all. We know that we cannot replace anything with a hash because we don't have any more hashes. Similarly for this. Do this. We had the second case running 4769. Let's see if we made it better or made it worse. Or made it the same. It's about the same. So this optimization didn't really optimize anything. Another idea that I have, yeah, it might have shaved off a little bit. I have a way how to test this. The primary metric that we actually have here is how many times did get configuration count actually gets called. So each time it gets called, I will just increase the call count by 1. And here we can say for the first part, well, reset the call count, log the call count, reset the call count, log the call count. This we don't need, we know that it's working. So if we comment out this line, now we're just making it a bit slower than usual. But the call counts are 119 and 3,050,000. So we have an algorithm that we are totally sure that it works. Only we need to reduce this number. We want it to be a bit less. So 119 and 3051. And we moved it down to 114 and less than 3 million. So we avoided 50,000 calls, which sounds like a lot, but it's actually 50,000 divided by 3 million times 100, 1.6% improvement. Well, to be honest, 1.6% improvement is nothing to scoff at, but it's nothing obvious. We need improvement by an order of magnitude, several orders of magnitude. So now let's think about what we can cache, so to say. Do we have some situations that are kind of repeatable? Because one of the things is that we are generating this by repeating the input. So we might be in a situation when we have something that needs to be remembered. For example, we can reuse this part because, yeah, this part, the answer to this part, with a group of 113, of course, is exactly 4. And we don't need to calculate that. So we need to check whether the tail end after something that's after this is already processed. Yeah, we might run out of memory about that, but let's see. We have a return here, and we have a return here, and let's add a bit of a cache. For now, let it be a string and a number. So, if my idea pans out, we might actually complicate things a bit first. Not that kind of a match, but pattern match. I will create another pattern match thing, so this thing returned true if the pattern matched completely. False if the pattern had no way of matching, regardless of whether it had contained question marks or not, or returned a null if it returned a question mark. But I want this to return actually something else. So when we get to the first question mark, we can say how far we got. We can say that we matched this part of the code, and it matched so far. So for example, we got to here, and we know that this part matches those groups. And then we are left, or we get to here, for example. So we know that this part matches that groups. And then we can just run our matching on this part. But we can only do that if the character before the question mark is a dot. Or do we? So let's think about it for a while. This has the pattern 113, 113, 113, and so on. So if we have this dot, dot, and everything else until the end, it is the same. So when we get to this question mark, we know that it cannot be a dot. Maybe we need to take care of that. To actually trim it as we go along. Or just say, well, we matched this part completely. Now I think I was right the first time. We might want to get to this point first. Can we detect that? So, if the hash count is 0, that means the character before the question mark was a dot. If we have a dot before the question mark and we got to the question mark, it means that we actually no, that is incorrect. We actually matched a fixed set of groups so far. So we have a, let's call it a stable situation. So we're in this scenario and we already matched a 113. So now we can exchange our problem for the problem of matching this string with, instead of 113, 113, matching this string with this. And this is maybe easier. And we can even use that once more because we will get to this scenario. And we can say that this is equivalent with matching this without the leading one. And on the other hand, if we do match this, and then we have a different situation, this will always be a solved problem. So maybe we want to take that into account. However, I think that I've gotten to a point when I want to commit this. So that I might be able to revert to this because I will doing some changes that might be kind of tricky. And I will stop this video now and I will see you in part 3.